Hello everyone. Today we are going to talk about another classical problem, LRU Cache. So the problem is to design a cache with a fixed capacity. We have two APIs, get and put, with key and value. If it is overcapacity, we need to remove the least recently used entry. So this is the key part of this problem. So let's look at more details. In the get API, if the key exists, returns a value. If the key is missing, we return -1. Also, a get call will make this key recently used. The put API has a key and a value. If the key already exists, we update this value. If the key doesn't exist, we insert an entry into this LRU cache. If it is full, we remove the LRU entry. So the goal is to support both operations in O1 time complexity. We need to maintain the LRU order efficiently. Step 1. So in order to do the fast lookup, we can use a map structure, for example, a HashMap with a key and value, so that we can do get and put in O1 time complexity. However, this is not enough. When there are multiple entries in this hash map, we don't know which one is the least recently used one. So we need to track the order of the usage. We want to use the most recently used one and to the least recently used one. So we need to maintain this order here. So whenever an entry is used, we want to move it to the head so that we can maintain this order. So naturally, this is a linked list. We have this order is from the most recently used one to the least used one. Whenever an entry is used, we move to the head. So the head is always the most recently used one, and the pair is always the least recently used one. However, there's another problem of, for example, when we access C, we need to move C to the front. But in order to move C, we need to connect the previous to the next. We need to find the B. So in the singular linked list, to find the previous node, we need ON time complexity, which does not meet this requirement. So how can we find this previous node efficiently in an O1 time complexity? We can use a doubly linked list. So whenever we get the node C, if we find the previous node, then we can directly connect to the next node. So remove can be O1. So whenever we get a node, we can connect B to D directly, so that it can be removed, and then we can insert the node to the head. So to summarize, we have two structures, one in the hash map to do the fast lookup, and we have a doubly linked list to do the fast reordering to do this LRU cache. Now let's look at an example. So initially, we have an empty LRU cache with capacity of 3. First, we make a call to put 1A. Second, we make a call to put 2B. So every time we make a put, we always put it to the head of the linked list. Now we put a 3C. So similarly, we also insert the node towards the head of the linked list. So it is always maintained this as most recently used node towards the least recently used node from the head to the tail. Now we make a get call to get 1. So we will move this node from the tail, from the original position to the head of the linked list. So now this linked list becomes 1, 3, 2. Now we make a call to put 4D. So we insert this 4D to the head of the linked list. But because the capacity is only 3, now we have 4 nodes. So we need to remove the least recently used, which is the tail of this doubly linked list. So this linked list will be internally we'll remove this 2. This linked list will become 413 like this. So this is the final state. So the key idea is every access will move the entry to the front. The entry at the back, at the tail is the LRU entry. When full, we just remove the entry at the back. Now let's look at the code. First, we need to define this node. The key into value, and we also have a previous. I also have a next. Read into value. So we set this key to key. Set this value to value. Now we will have a map integer node map. We also needed this capacity. We also needed the head, the material, which are common techniques usually in linked list, and this will be needed for us to keep track of this doubly linked list. So in the constructor, we set list.capacity equals to key dt list.map equal to initialize this map list.dummy head equal to new node table dot tail to new novel yellow, and we connected the dummy head dot next to place dot dummy tail dot dummy tail dot fe dot is dot dummy head. So put in the get call, we should try to see if it exists in the map. If it does not exist in the map, then connect to 1. Straightforward. Now, once it exists in the map, as we said, we need to move it to the head. So the first step is to remove from list. No. So node.previous.next to node.next. We connect the previous one next to the next node, and we connect the next node dot previous equal to the previous node. So we first move towards from this. Then what we need to do is to insert to head. Set to head. So when we insert, we first need to connect to the true head. So equal to dummy and dot next and dummy head dot next dot ev is equal to the node. Now we want to connect this node towards dummy head. Node dot previous equals to dummy add the head or next equal to node. So we want to insert these to the head and return over the value. So input, we first also try to see if this node already exists or not. If it already exists, we will need to update it. So node.value equal to value. Now, because we have access to these nodes, so we also need to move it to the head. So we also need to move from this node insert to head node. Else, if this doesn't exist, what we need to do is create a node, new node, key value, and first need to put it to the map. Dot port key node. Now we need to insert it to the head. Insert it to head node. Now we need to check if the size has exceeded the capacity greater than capacity. If yes, we need to remove the tail. And is given from list dummy tail dot previous, and we also before that we need to remove it from the map. Otherwise, the dummy tail dot previous will be updated. Dummy tail will be updated during the remove list. So map dot remove the tail dot free dot key. So let's see, if it's greater than the capacity, we first remove it from the map, and then we'll remove it from the remove the tail from the doubly linked list. Let's walk through this code again. Pulled, we try to see if it already exists. If it already exists, we update this value and we remove from the linked list and then move it to the head. Otherwise, we create a new node, put it into the map, and insert it in towards the head. Then we check the capacity. If we need to remove the last node. So when you first remove it from the map and then remove it from the list. In the get API call, we check if already exists. If not, return -1. Otherwise, we remove it from the list and then move it to the head. Remove from list is connecting to the previous .next equal to the next node, and the correct next .previous equal to the previous node. For the insert to the head, we first connect on the next to the current true head, and also connect the current true head .previous equal to the node, and we correct node .previous equal to the dummy head and dummy head .netted. So let's try to run the code. See, so all the random test cases had passed. I tried to run this random test cases. Yeah, all the test cases have passed. So now we have finished with the code implementation using a HashMap and doubly linked list. And every time, the key idea is every time when we access a node, we remove it from the list and insert it to the head. This applies both for the get call and then pro call for the update operation. For the insert operation, we insert it to the head and approve it to the map. When the size is over the capacity, we'll remove it from the map and also remove it from the doubly linked list. Yeah, that's the idea of an LRU cache using a map and not doubly linked list. Hope you find this video useful. And if you have any questions, welcome comment. If you like this channel, welcome subscribe. Thank you.